So right now we'll be doing the second question in the homework 9 for probability and stochastic processes. The second question says that we have a Poisson process with the parameter lambda, and then the process is that n, which is the number of points within the period t1, t2 is k, and that's given by e to the power minus lambda t2 minus t1 into lambda t2 minus t1 to the power k by k factorial. And we're also told that xt, that the process is equal to 1 if the number of points within that interval is odd, and if it's minus 1 if the number is even. So we get to know about that from here, right? So now we start the question. And the first part says that we need to draw a couple of samples. So as we can see from the function, this is a typical telegraph signal. So the samples for a telegraph signal are as follows. So we get a 1 when it's odd and the number of samples is odd, and minus 1 the number of samples is even. So that's fine. Then we get the second part, which says that we have to find the probability that x of t is equal to 1. That means that the number of points within it is actually odd. So as the number of points is odd, so we get all various combinations as p1, 3, 5. So this is the number of points is 1, 3, 5. Basically all are odd. So when we actually open this up and write in terms, we get e to the power minus delta lambda t, that comes out to be common, and then to the power n by n factorial, where n is this number, so it's like lambda t to the power 1 by 1 factorial, that's the same thing as lambda t, and then lambda t cubed by 3 factorial, that's the same as this. So we add all of these up and we end up with e to the power minus lambda t into sine hyperbolic of lambda t. This is the second part. The third part says that we have to find out the expected value for xt, that's the mean. Now to find out the expected value, we have e to the power minus lambda t into sine hyperbolic lambda t minus e to the power minus lambda t into cos hyperbolic lambda t. So when we actually solve this out, what we get is we get e to the power minus lambda t common, we get sine hyperbolic lambda t minus cos hyperbolic lambda t, which can also be written as actually cos hyperbolic lambda t minus sine hyperbolic lambda t can be written as e to the power minus lambda t. So we get this minus sign and we get the power 2 over here. Also, now we see the fourth part, which tells us to find the autocorrelation function for t1 and t2 for xt. So for that, we can actually see there can be 4 cases. Now the 4 cases are that when xt1 is equal to 1, when xt2 is equal to 1, and then xt1 is equal to minus 1, when xt2 is equal to 1. So we get the second one over here. Then we get when xt2 1 is equal to minus 1, and then t2 will be minus 1 and 1 respectively. So we have 4 cases in total. In 2 of these are in which xt of 1 will turn out to be 1, and 2 are in which xt1 will turn out to be minus 1. So we actually compute the expressions for all of these, and so the one for xt1 equal to 1 when xt2 is equal to 1 is also over here. So we get that from here. When we actually combine all of these together, what we get is the autocorrelation function, and that is actually minus e to the power minus 2 lambda t2 minus t1 minus t2. T1 minus t2 can be also written as t2 minus t1. Is basically the time difference, which is usually denoted by, in this case, t or usually tau.